Welcome class. Well, today's lesson is about projectile motion at an angle. It's a follow-on from previous lessons where we looked at projectile motion launched horizontally. And I have been buoyed by recent events over in Pyeongchang in South Korea. So thought that I would start the topic of conversation by looking at a Winter Olympic event. Which has a lot to do with projectiles. So the event that I've chosen to talk about is the event which is wonderfully known as the biathlon. And those that are not familiar with this event, well, just to give you a little bit of an introduction to it, it involves skiing and shooting using a rifle. And in my mind is one of the most grueling sports that is out there. So people, competitors that is, are tasked with the unenviable task of skiing 20 kilometers with a 3.5 kilogram rifle on their back. Now we're not going to convert 3.5 kilogram rifle and look for the weight of that in newtons, of course, but it's pretty heavy. And not only do they have to do that, which takes a huge amount of effort and energy, they have to stop at regular intervals and shoot at 5 targets 50 meters away. So you can imagine the heart rate pumping and then having to stop and steady yourself and shoot at these tiny targets. So there's no doubt about it, these competitors need ice in their veins. So the question that I have for you folks is this. The question to ponder is the shooter aiming at the target? So does the shooter in the biathlon, do they in fact aim directly at the target? So when they're lining up the shot, do they aim directly for the target and the projectile just goes in a straight line? Or would they have to aim above the target or below the target? So if you've got any basic knowledge of projectiles, you should know that the line that was drawn earlier is not strictly speaking how projectiles work. So we would need to maybe get rid of some of this line because usually projectiles are under the influence of gravity in the y direction, in the vertical direction. And what's more likely to happen, in fact, is, and we know this anyway through anecdotally through our actions and from our experiences in life, we'll see that it will start to dip. Now, the question of how the athletes actually have to prepare and where they aim their rifle at, well, that depends on a lot of things, namely the velocity of the bullet as it leaves the gun. But projectiles will drop, and the reasons why those projectiles drop, of course, is because of acceleration due to gravity, which on Earth we say is a standard 9.81 meters per second squared. So just to recap on a couple of things, we're going to talk about projectile motion and some of the important concepts. Some of the things that we should know, hopefully, at this stage in our physics development. We should know a couple of things. We should know that we assume the only force acting on projectile is gravity unless otherwise stated. In high school physics, usually the only force that's acting in a projectile scenario is the force of gravity, which acts only in the vertical direction, or rather it acts on the object in the direction causing the object to move towards the ground. The second important concept is that uniform motion is exerted in the x-axis. That is to say, if we look at the projectile vector that we've drawn and we look at the red arrows, and I sort out my numbers here, which are pretty poor at the moment, we see that at some time intervals, and I'm just going to number them 1, 2, 3, 4, 5. If we took a look at the vector just in the horizontal, the x-axis, because there's no external force acting in the x direction, and therefore, according to Newton's first law, the object will just keep moving with the same velocity. So that velocity is uniform, and you can see that by the size of the red arrow remaining uniform. The third point is that acceleration due to gravity is in the y-axis. So there will be acceleration in the y-axis. So there is no velocity in the y-axis at the beginning point, number 1. Number 2, in the y, we see that there's the beginnings of a velocity downward. And if we move to 3, 4, 5, we see that that velocity vector starts to increase. And that is because there's acceleration in that direction. So just to recap, and also the fourth important concept is that time is the only variable that is the same in the x and y axes. In other words, at time interval, or at interval number 3, the time in the x-axis and the y-axis is the same. The delta t that is taken for that object to from the beginning to reach interval number 3 is the same in both axes. So just to recap, in the x-axis we have uniform motion, no acceleration. Therefore we can use the equation Vx is equal to delta dx over delta t, or delta x over t. However, in the y, we do have acceleration. We cannot use that simple equation, which ignores acceleration, or talks about acceleration being 0. So in the y-axis, we need to use what are called, we sometimes call the big 5 or the kinematics equations. And we'll only use those in the y-axis. Okay, so let's look at a projectile at an angle example. And we're going to return to our good friends over at South Korea, at Pyeongchang, to look at another event in the Winter Olympic calendar, and that is ski jumping. Another brave event, brave souls jumping around in the ice. If we look at ski jumping, we have competitors launching themselves off a platform at a specific angle to the horizontal, and therefore they're exhibiting projectile features, I guess. So they're launching themselves in the green, the trajectory denoted by the green arrow. And they usually do that at an angle to the horizontal around 35 degrees. So if we look at this scenario, that is a projectile scenario, but we're going to start by looking at a slightly simpler one, because those particular athletes land underneath where they took off. So there is a difference in height from where they began and where they finished. But let's look at a simpler example of a projectile at an angle first. So for a projectile launched at an angle, we have to look at certain things and talk about the certain things. First thing is that vi, the initial velocity vector, can be split into its x and y components using trigonometry. If we have Vix, we also know that Vfx is going to be the same value, because we already talked about the fact that the velocity is uniform. And we can also use trigonometry to break this Vix into its x and y components. So if we break it into the x, on the x side, we can see quite clearly that Vix is equal to Vi cos theta, just using that triangle at the beginning. And if we look at the y direction, we can also see a couple of things, and I'm going to explain why in a second, but we can also see that Viy is equal to negative Vfy. In other words, those velocity vectors beginning and ending in the vertical are the same magnitude but the opposite direction. Now, let's have a look at what we know. So we know the initial velocity in the x direction, and for the same reasons, we can say that Viy is equal to Vi sine theta. Again, back to trigonometry in that triangle on the left. And we also know the acceleration vertically is negative 9.81 meters per second squared. So we know that if we can just figure out one more variable in the y, we would have 3 variables, and we can use the kinematics equations, the big 5, to get whatever variable we want. So what are the strategies available to us when solving such questions on projectiles at an angle? Well, we can use the fact that VIY is equal to negative VFY, and we can use that fact to get t by using the equation acceleration is the final velocity minus the initial velocity over delta t, and just use some algebra to rearrange. And we can get our value for time, a very, very useful variable, because if we have the value for time, that now can go into the x side, and we can use Vix and time to get our displacement in the x, just using the uniform equation, the easy equation, Vx is equal to delta d over t. The other thing that we might want to do, or might want to consider, is using VIY equal to delta VFY to get delta D. And if we have a look at that to get delta D, what we'll notice is delta dy is equal to 0. In other words, the projectile has begun and ended at the same vertical point. And so that makes this thing here 0, and this whole 2a delta D 0. Which actually shows us that VFY and VIY are VFY squared and VIY squared are equal. So that magnitude of those is equal, and the squares take care of the negative and plus sign. So it sort of bears out the fact, as we talked about, that VIY is equal to negative VFY. The second thing that we could choose to do is to use the fact that delta dy is equal to 0, in other words, the projectile started and ended at the same vertical point, and solve a quadratic equation for t. So if we look at the equation before us here, and we know that delta dy is equal to 0, we can do some manipulation here, and we can rewrite that as a half at squared plus VIYT is equal negative delta dy is equal to 0. Okay, and we can solve for t. So we have a similar to, you would see an x squared, x, and an x squared here, an x value here, and then we would have our non-x value, I guess. Now that you can see is quite easy when delta dy is equal to 0. But even if this delta dy value is not equal to 0, it is very useful, because that if the delta dy is non-zero, it means the projectile has finished at a height value that's above or below where it started. And very often you'll see questions like that in angle projectile problems, and you would need to put in an actual value for delta dy, and you'd need to solve using a quadratic. You can still solve for t, and that will allow you to get various other values, because we can now use it in the x. Okay, so let's look at an example here. We're just going to look at a very quick example. A rock is thrown from the edge of the top of a building with an initial velocity at 12 meters per second at 50 degrees. The rock strikes the ground 25 meters from the base of the building. So in other words, we know what our delta x is, and that's in the horizontal. Assume the ground is level and the building side is vertical. How tall is the building? Okay. So what we're essentially looking for is how much this projectile is falling, the delta dy. Okay, so what do we have in the x? Let's write down what we have in the x direction. We have delta x is equal to 25. We also have the Vix value, because we know it to be Vi cosine 50 degrees. And we know that in this case the Vi is 12 meters per second, and we need to split that up into just the x portion, and we can get a value for that. And we also know that on the other side, we also know that we can get on the y side, we can ask ourselves, okay, well, what do we have and what do we need? On the y side, we have a y is equal to negative 9.81 meters per second squared. Of course, you can use positive there, but generally the downward direction is a negative. And we also know that VIY is equal to 12 sine 50 degrees. Okay, and we can figure out what the VIY value is. Now, if we go back to the x direction, you can see that we've got two variables. We have 1 and we have 2. And of course, we know that Vx is equal to delta x over delta t. Therefore, we also know that delta t is equal to delta x over Vx. And that would allow us to get the delta t value if we know Vix. On the y side, once we've discovered what the t value is, we can now use that delta t value because it's the same in the y, and that would give us, in the y side of things, it would give us three variables also, 1, 2, and we would have the delta t, which would be our third value. So that would mean that we would have three values, and when we solve for that delta t value, we can actually use our big 5 to get a delta dy. So which one of the big 5 equations would we use? Okay, if you said that you would use delta dy is equal to VIYT plus a half AT squared, I would say yes, correct, because bearing in mind that we're looking for the delta dy, we have VIY, we have t, we have a, and we have t. So that would allow us to get our delta dy value. So let's actually work this out, and we can figure out that Vix, if we work it out, it will actually give us a value of 7.71 meters per second. And when we put that through the mill to get delta t, we get a value of 3.24 seconds. Now we can bring that 3.24 seconds because we know t is shared in the x and y, and it's a lovely intermediary. And we've got three of them, so we can now solve for delta dy. And we say it's equal to VIY, which is 12 sine 50. So we just got to put that into a calculator, and we're going to get 9.1. So what we're going to get here is 9.19 meters per second for our VIY value. And we multiply that by 3.24, and we get 29.78. Excuse the different color font. We have a half a, which is going to be negative 4.9, multiplied by t squared, which is going to be 3.24 squared. 4 squared. Okay, so if we get our 3.24 and we square that, we get a value of 10.4976. We multiply that by 4.905, and we get a value of negative 51.49 meters. And of course we keep our first part in there, and what we're going to get is we're going to get a value which is in the negative. Should that be a surprise to us? Well, it should not be a surprise, because we finished up below where we started. So we get a value of 21.71 meters. And if we go back to that question, what that means is that the drop here was 21 meters, okay? And 21 meters in the negative. Okay, so I'm just going to finish with one challenge problem. Trickier challenge problem is here. I'm just going to set the problem and then leave it with you to finish. Again, it's a ski jump problem. The problem is a little bit harder because if you follow the green trajectory, the ski jumper lands below where they began, and there's also a slope to contend with. So the problem is Janice Jumperson leaves a ski jump ramp at 24 meters per second at 35 degrees above the horizontal. The slope is inclined at 50 degrees and air resistance is negligible. So we've taken into account that this slope that Janice is going to actually land on, that the angle is 50 degrees. Find the distance from the ramp to where the jumper lands. So if the jumper lands along the slope here, it's that distance between these circles. Now just a little hint in terms of answering this. My top hint is to remember that delta dx is equal to Vix delta t. Okay, so I'm just going to leave this particular problem with you guys to solve, and we'll take it up tomorrow.